Hi everyone, here's a great application of dot products. We can use it to find the angle between two vectors. So let's say that we have two vectors, v and w, neither one being the zero vector, because the zero vector has all angles in a way, right? You can associate any angle to the zero vector. Let's say we have two vectors, v and w, and they don't even have to be connected. I could just draw a vector v, an arrow like this to represent v, an arrow here to represent w, okay? And I can talk about the angle between two vectors. Now, it might be helpful to place their initial points together, like at the origin. So it may be helpful to put the v vector here, the initial point at the origin, the w vector here, the initial point at the origin, to help orient ourselves. And we could talk about the angle between these two vectors. And in fact, we can take the least non-negative angle between these two vectors, the least non-negative angle. Okay. Which means that the angle can be said to be somewhere between 0 degrees and 180 degrees. For example, let's say that we have a vector pointing east. Well, if you rotate it over here, right, this guy here is pointing the opposite direction. There's a 180-degree rotation between these two vectors. But if you were to rotate this a bit more, counterclockwise, so it's like that. See, back in chapter 4, we might have said that this was like a 200-something degree angle, but no. If the vectors are in these two directions, then this angle here would be taken to be the least non-negative angle between them. Okay, so this here. We take this counterclockwise angle, positive angle, from here to here. Okay, so in that sense, the angle between two vectors can always be said to be between 0 degrees and 180 degrees. And we're assuming they're non-zero, because the zero vector, again, has all angles associated with it. Kind of like if you take the Earth, right? The North Pole of the Earth is on all possible longitude lines. Okay, anyway, let's say that this angle is theta. We remember him. Let's call this angle theta between the two vectors. Okay, don't confuse that between the direction angle. Although you could get theta by taking the direction angles for the two vectors and subtracting. You could do that. But we're going to use this formula. Theta is the angle between the two vectors. So cosine of theta is given by this formula. And a great way to remember it, it's the dot product, v dot w, in either order, right? In fact, I don't care which one you call v, which one you call w, right? This could be v, this could be w, or vice versa. It's going to be the same angle, all right? Commutativity, we can switch these. It's the dot product over the product of the lengths. And again, you could switch these, but don't switch the top and the bottom. All right. It's the dot product over the product of the lengths. The dot product is a scalar, and lengths are scalars. And we're assuming that we don't have the zero vector for v or w, so these guys will not be zero. The dot product could be zero. We'll see that later. But we know the lengths will not be zero. Okay, so the cosine of theta is given by this formula, the dot product over the product of the lengths. There's something called the Cauchy-Schwarz inequality, which guarantees that this will always spit out a value between -1 and 1. Which means, by the way, when you apply inverse cosine, because theta, you might wonder, can we say it's the inverse cosine of this whole jazz over here? And this time, I'll put a blue arrow here. This time, the answer is yes. We can use the inverse cosine notation. Now, some books may still hesitate because, remember, many books say that if you have inverse sine, inverse cosine, inverse tangent, the result should be written in radians. I don't have that rule. I'm okay with you using inverse cosine notation and then giving me an answer in degrees. I'm okay with that. Okay, that's the least of our worries, I think. I'm worried more about quadrant. Now remember, when we were dealing with inverse tangent before, right, we had a potential problem with quadrant. But here we're not going to have a problem, because what's the range for inverse cosine? The range for inverse cosine is from 0 to pi radians, or what in degrees? 0 degrees to 180 degrees. So when we apply inverse cosine, we're guaranteed that we're going to get an angle in the appropriate interval. So inverse cosine is perfectly fine, again, assuming that neither of these is the 0 vector. And if, like me, you're okay with the answer being given in degree mode, in degree measure. All right, so inverse cosine works perfectly. We don't have any range problems like we could have had with inverse tangent, like we did in that one example. All right. Here's another great thing about the dot product, and it's related to this over here. By the way, in case you're wondering how it's proven from the law of cosines. So it's kind of appropriate that the law of cosines was also in chapter 6. This is proven from the law of cosines. All right. A great fact. Two vectors, v and w, are orthogonal. I know that's a tough-looking word, but when you see orthogonal, think perpendicular. Orthogonal is a fancy way of saying perpendicular. They're frequently interchangeable. But bear in mind that in Math 254, linear algebra, you're going to define inner products in such a way that you can talk about polynomials being orthogonal. That's kind of mind-blowing. But for right now, geometrically, think of orthogonal as meaning perpendicular. All right, like for example, here's a vector v, and here's an orthogonal vector w. And it turns out that two vectors in the plane are orthogonal or perpendicular if and only if the dot product in either order is the scalar 0. By the way, this works for 3-space also, if these vectors are in 3-space. So remember, for non-zero vectors, these lengths cannot be 0, but the dot product could be 0. That happens if and only if the dot product is 0, if and only if the vectors are orthogonal or perpendicular. It's a nice test for perpendicularity or orthogonality if the dot product is 0. Now let's see why that is. You can get it from the nature of this formula, okay? Cosine of theta, I'm going to go ahead and erase a lot of these annotations here. Kind of a mess, all right? Okay, let's focus on this formula. Cosine of theta equals the dot product over the product of the lengths, all right? Now here's the deal. These vectors are non-zero. We know that lengths, if they're not 0, they're going to be positive, right? Lengths are positive. Magnitudes are positive, which means that the sine of cosine of theta is determined entirely by the sine of the dot product. And the cosine of theta will be 0 if and only if the dot product is 0, because these pieces down here are both positive. The sine of this is the same as the sine of this, SIGN, or they're both 0, right? Well, let's think about cosine values, right? So again, what I'm saying here is that the cosine of theta has the same sign as the dot product between the two vectors, all right? So let's remember the deal. In chapter 4, okay, let's say we have an acute angle. If we have a quadrant 1 angle, all right, then what is the sign of cosine? Cosine is positive. Also, cosine of 0 degrees is 1. Okay, it's also positive for this quadrantal angle. Cosine of 90 degrees is 0. Remember COS. COS. Cosine of 90 degrees is 0 up here, right? And what's the sign, SIGN, of cosine in quadrant 2? What's the x-coordinate in quadrant 2? It's going to be negative. And the cosine of 180 degrees is -1. So cosine is negative for this quadrantal angle. And we're only worried about angles, remember, between 0 degrees and 180 degrees, right? We're saying that the angle between two vectors can be said to be somewhere in here. So what that means is that, I'll put this in green. That means that cosine of theta is positive if and only if the angle between the two vectors is quadrant 1, in particular, acute, strictly between 0 degrees and 90 degrees. Or it could be a 0 degree angle because cosine of 0 is positive 1. By the way, what does it mean for the angle between two vectors to be 0 degrees? Let's say we have an angle, a vector here. Let's say we have a vector here. Draw for me an arrow representing a vector that makes a 0 degree angle with this vector. Basically, draw for me a vector that makes a 0 degree angle with this vector. Any vector that points in the same direction. And by the way, the 0 vector is orthogonal to everybody, right? You could have talked about the 0 vector, but the 0 vector has all possible angles, right? We're focusing on non-zero vectors. If you have two vectors pointing in the same direction, so they're parallel and pointing in the same direction, then the dot product will be positive, right? In that case also. Or you have an acute angle between them. So the cosine of theta, that is the dot product, is positive. So when I say the cosine of theta is positive, I'm also saying that the dot product is positive in the case where the angle is acute or if there's a 0 degree difference, meaning that they're pointing in the same direction. All right. Now, what about the case where cosine of theta is negative? If cosine of theta is negative, I'll do this in orange. Cosine of theta is negative if and only if the angle is obtuse, strictly between 90 degrees and 180 degrees, right? A quadrant 2 obtuse angle. Or remember, cosine of 180 degrees is negative 1, that quadrantal angle. Or we have a 180 degree angle. So we have two vectors that either form an obtuse angle, like so, or there's a 180 degree angle between the two vectors. By the way, folks, these are fair test questions, so pay attention. What does it mean for a vector to form a 180 degree angle with a vector like that? The vector has to point in the opposite direction. Now, see, in both cases, in this case here, in this case here, and in this case here, the pairs of vectors are parallel in both cases. If they point in the same direction, the angle between them is 0 degrees. If they point in opposite directions, the angle between them is 180 degrees, okay? So it's not enough to say that two vectors are parallel. All right, anyway. Oh, and what happens if the cosine of theta is 0? Do that in red. That was the key point here, right? That was the most important case, all right? If the cosine of theta is 0, if the cosine of theta is 0, right, that means the dot product is 0, okay? That means and by the way, this is also a statement on dot product, right? Okay, over here, cosine of theta is 0. That is the dot product is 0, right? Remember that we got that from this formula here. Cosine of theta is 0 if and only if the dot product is 0 for non-zero vectors, okay? The cosine is 0 if and only if the angle is COS 90 degrees. We have a right angle between them, which means that they're what O word? The two vectors are orthogonal or perpendicular. That's when the cosine of theta is 0. That's when the dot product is 0. So here's a great application of dot product. The sign of the dot product, okay, just by getting the dot product, you can find the nature of the angle between them. If I have two non-zero vectors, v and w, and you take their dot product, v dot w, if the dot product is positive, the angle between them is acute or 0 degrees. They point in the same direction. If the angle between them, if the dot product is negative, that means the angle between them is obtuse, or they point in opposite directions, 180 degrees. If the dot product is 0, that means you have a right angle. Again, that's this over here. Two non-zero vectors have a 0 dot product if and only if they are orthogonal or perpendicular. Great rule. And again, the sign of the dot product tells you the sign, SIGN, of the angle between them right off the bat. But what if we want the actual angle? Okay, let's go through the formula. Find the angle between these two vectors. It's helpful to think of them as position vectors, represented as position vectors, using equal scaling on the axes so we can visualize angles. 2, 1, kind of flat, right? And -2, -3, that's a bit steeper. Okay, we have a quadrant 1 vector and a quadrant 3 vector, if you think of them as position vectors. So you can see the angle between them. If we drew these kind of right, we're guessing we're going to get an obtuse angle between these. Now, I didn't draw them very accurately, but just from a quick sketch, I think we're going to get an obtuse angle. Again, you need equal scaling to have a good sense of what the nature of the angle is. If you have unequal scales, you can distort pictures. Remember, if you have unequal scales, then this could be a square with perpendicular diagonals. So be careful. If you want to visualize angles, you better have equal scales on these axes. All right. Well, here's a more accurate sketch. I did it freehand. It turns out that if you do graph these position vectors, yeah, you can see visually the angle would be obtuse. Notice that I have equal scales on the two axes. Very important if you want to try to visualize angles. I mean, parallel will stay parallel, but you can't even determine perpendicular vectors if you don't use equal scaling. All right. Let's work this formula. The cosine of theta equals the dot product over the product of the lengths. Here, I indicate what V and W are. I'm just plugging them in. How do you find a dot product? Okay, as work, you should tell me what the dot product is. It's this times this plus this times this. What's 2 times -2? It's -4. What's 1 times -3? It's -3. Again, I like to write down the products instead of going 2 times 2 and so 2 times -2 and so on. See that? I often miswrite things, so I like to do the products in my head. 2 times -2 is -4. 1 times -3 is -3. And then you combine. -4 minus 3 is -7. That's the dot product. And notice this is negative. So right off the bat, what can we say? The dot product is negative. So that means that right off the bat, we know that the angle is going to be obtuse, right? Because cosine is negative in quadrant 2. Okay, the angle is going to be obtuse. Or they point in opposite directions. But the thing is, these are not scalar multiples of each other. So they're not parallel. They're not scalar multiples of each other. So we know the angle is going to be obtuse. Okay, which we can see from our sketch picture. Well, my sketch or from a computer. Okay, these lengths, remember, it's Pythagorean. The square root of 2 squared plus 1 squared, all right, times the square root of the square of -2. Remember, squares are never negative. The square of -2 is +4. Put the grouping symbols here. Plus the square of -3. Okay, this here is root -5. Better not be -5. This here is root 5. This here is root 13. All right. Now, you could work this out, but be careful. There's a double division here. You're dividing -7 by this and this. So it might be better to multiply the radicals. That does work. Root 5 times root 13 is 5 times 13 is 65. That does work. All right. For some reason, I rounded off here, but that's a bad idea. I shouldn't have done that. Whatever this is, keep the decimal approximation on your calculator, all these sig figs. It won't be exact, but it'll be very accurate. I shouldn't have rounded here. Okay, don't round off unnecessarily in the middle. Anyway, cosine of theta turns out to be this negative number, right? What button do you put on your calculator? You see a number like this in your display with more sig figs? Cosine of theta equals these guys here, right? What button do you press to get theta itself? You want the inverse cosine or arc cosine. And make sure you're in degree mode because we want to express our angles in degree measure, usually in chapter 6. All right, so theta, and remember, you can use the inverse cosine notation. I say it's okay to give your answer in degree mode. Books may object because they usually like to have these results in radian measure. I say this is okay. The inverse cosine of this guy, right? All right, and you get about 150.3 degrees, which is What kind of angle? It's an obtuse angle. And it seems to be consistent with our picture here. It makes sense that this is about 150 degrees, right? 150.3 degrees. That's the angle that separates these two vectors. Whether you orient them as position vectors, if you use those, whether you use those representations or not. Remember, I can move this vector here, move this vector here, and the angle between these two vectors will still be this here. So using dot products to find the angle between two vectors. Next, we'll talk about applications to physics.